Hello, Stat 200, and welcome to Lesson 12. This week, you're going to be learning about correlation and simple linear regression. You were first introduced to these topics at the end of Lesson 2. Now that you know more about statistical inference, we're going to revisit these topics this week. These are the key topics that you're going to learn about this week. First, we'll review scatter plots. We'll learn how to compute a correlation coefficient. Then, we'll learn about simple linear regression. And finally, the coefficient of determination. Let's start by reviewing scatter plots. A scatter plot is a graph that's used to display the relationship between two quantitative variables. A scatter plot can be described in terms of direction, so whether it's a positive or a negative relationship, form, whether it's linear or curvilinear, strength, and outliers. Let's look at a few examples. Here we have a scatter plot showing the relationship between height in centimeters and weight in kilograms. In terms of direction, we have a positive slope. The form is linear. In other words, if I was to draw a line of best fit, as we have here, a straight line would be the best line of best fit. The strength I would describe as moderately strong. This has to do with how far away all the individual points are from that line of best fit. And I would say there are no clear outliers in this scatter plot. Here we have a scatter plot showing maximum daily temperature and the number of cups of coffee sold at a student-run cafe. The direction is negative, so as the maximum daily temperature increases, so as it gets warmer outside, the number of coffee sold decreases. The form is linear, the strength is moderate, and there are no clear outliers. Here we have a scatter plot of anxiety levels and scores on a test. The direction of this scatter plot I would describe as flat to positive. So when anxiety is between 2 and 5, we have a flat line, so no relationship at that point. But then once you get past an anxiety score of 5, as you're going from about 5 to 8, we have a positive relationship. This is not a linear relationship. I would describe this as a curvilinear relationship. The strength is strong, and there are no clear outliers. We have one last example. Here we have a scatter plot showing the relationship between elbow diameter and age. These data were collected from a sample of American adults who regularly attend the gym. In terms of direction, I would say that there's no relationship here. So there is neither a positive nor a negative direction to this plot. I would just describe the form as a blob. If we were to draw a line of best fit, we would just draw a flat horizontal line that goes through the mean of X, or the mean of age. Because regardless of what someone's elbow diameter is, that doesn't really give us any information to better predict their age. In terms of strength, very weak or no relationship. And there are no clear outliers. If you're looking for a review of scatter plots, or if you want to see the directions for how to make one in Minitab Express, you can go back to the Lesson 2 notes. This would fall under the category of two quantitative variables. Next, let's look at correlations. This is the conceptual formula for your online notes for Pearson's R. There are many different types of correlations that you could compute. Pearson's R is the only one that we're going to look at in this course. It is by far the most commonly used correlation coefficient, and it is used when you have two quantitative variables. So X and Y must both be quantitative variables. In terms of testing for statistical significance, the sampling distribution that we used to find a p-value to determine whether or not a Pearson's R correlation is statistically significant or not is a t-distribution with n minus 2 degrees of freedom. I'm going to go to StatKey now, and I'm going to construct a sampling distribution for correlation just to show you what it looks like so you can see why the t-distribution is used with correlations. In StatKey, to demonstrate this, I am going to do a randomization test for a slope or correlation. Later, we'll see simple linear regression. When you have a simple linear regression, you just have one x and one y variable. So testing for the statistical significance of a Pearson's R correlation and the slope in simple linear regression is actually very similar. You'll get the exact same p-values regardless of which of those you're testing. So to demonstrate this, I'm going to use the restaurant tip as a function of bill data set. When we're doing a randomization test with two quantitative variables, what's happening is StatKey is randomly selecting one x value and one y value, putting them together to make a point. So, for example, here we have 71 and 4. If we go to the original data set, we can see where the x value is coming from. Here we have 71, and then 4, we have lots of points that have a y value of 4. So in this case, we don't know which one it's coming from, but that is where the 71 and the 4 are coming from. If we click Show Data Table, we are given an entire list of all 157 x and y combinations that were randomly put together. So we'll generate a few thousand samples, just like we did in previous lessons when we were doing one sample tests. We can see that the sampling distribution of R, essentially, so all of our different correlations within these randomization samples, they should have a mean right around 0, because the null hypothesis is that there is no correlation. And the shape will be approximately normally distributed. So for that reason, when you're conducting a hypothesis test, or even if you wanted to construct a confidence interval for a correlation coefficient, the sampling distribution is going to be approximated using a t-distribution. And again, the degrees of freedom for that t-distribution will be n minus 2. Let's run through a few facts about correlations. You've seen most of these in lesson 2. And then, like I said, we'll go to Minitab Express and we'll construct a correlation matrix. Correlations must be between -1 and +1. If R is greater than 0, the relationship is positive. In other words, there's a direct relationship. If R is less than 0, the relationship is negative. In other words, an indirect relationship. As R approaches 0, the relationship becomes weaker, and as R approaches -1 or +1, the relationship becomes stronger. Correlations are unit-free. Recall, we computed the correlation between height in centimeters and weight in kilograms. So your x variable and your y variable can be on different scales. When you compute the correlation coefficient, you're going to convert both of them to z-scores anyhow. So the original scale of measurement does not matter. X and y are interchangeable. The correlation between x and y is the same as the correlation between y and x. And finally, the sampling distribution is approximated using a t-distribution. For the most part, you should not need to compute the t-test statistic by hand. When you run the correlation within Minitab Express or any other statistical software, it will give you the correlation and it will give you the p-value. Just know that the p-value that it's giving you is based on a t-distribution. Let's go to Minitab Express now and construct a correlation matrix. The data set that we're working with here contains data concerning a sample of Stat 200 students. We have each student's Wiley Plus average, their quiz average, lab assignment average, and their midterm 1 score. Let's construct a correlation matrix to examine the relations between these 4 variables. In Minitab Express, correlations are going to be found under the Regressions tab. Now, we could just compute all of the pairwise correlations one at a time, so we could do the relationship between Wiley Plus scores and quiz scores. This is what our output will look like then. So we have 2 variables, Wiley Plus and quizzes. R equals 0.742 with a p-value that is less than 0.0001. Because this p-value is less than the standard alpha level of 0.05, recall we would reject the null hypothesis, and in this case we would conclude that there is a statistically significant relationship between Wiley Plus scores and quiz scores. In other words, here we have a sample of data from approximately 34 students. There is some missing data in here, so we have complete data, I believe, from 32 students. So in our sample of 32 students, this is R, the sample correlation. And with our p-value, we can conclude that there's evidence that in the population, so in the population of all Stat 200 students, there is a statistically significant relationship between these 2 variables. Now, Pearson's correlation coefficient is just the relationship between 2 variables at a time. We could go through and do all of these correlations pair by pair, but with 4 variables, we'd have a lot of correlations to do one at a time. Minitab Express will compute or construct a correlation matrix for you. The matrix will give us all 6 possible pairwise combinations of these 4 variables. So again, we've already looked at the relationship between Wiley Plus scores and quiz scores. Let's look at the relations with midterm 1 scores. A lot of times in educational settings, we want to be able to predict exam scores. So here we have the relationship between Wiley Plus scores and midterm 1 scores. It's a moderately strong relationship, statistically significant. Here we have the correlation between quiz scores and midterm 1 scores, a little bit stronger. Again, it's a positive relationship. We have our p-value, so this is also statistically significant. And finally, the relationship between lab assignment scores and midterm 1 scores. Slightly weaker than the other relations, but again, it's a positive relationship and it is statistically significant. So in each cell, right, we have lab assignments, midterm 1, we have Pearson correlations on top and p-value at the bottom. If we look at cell contents, this is our key to seeing which cell is Pearson correlation and which is the p-value. In addition to correlation, the other big topic that you're going to see this week is simple linear regression. If you need a review of drawing a line, see the end of the Lesson 2 overview video. Here's your formula for a simple linear regression line in a sample. Y hat is the predicted value of y. B sub O is your y-intercept, and B sub 1 is the slope. X is your explanatory variable, and y is your response variable. In simple linear regression, x and y are not interchangeable. X must be the explanatory, and y must be the response variable. Because the way that this equation works, we're using x to predict y. The y-intercept, recall, is the predicted value of y when x equals 0. This value is useful in some scenarios. So if when x equals 0, if that has some sort of meaning, then the y-intercept would have a meaning. In a lot of cases, this is not a meaningful value though. So for example, if I wanted to compare your SAT math scores and SAT verbal scores, say I wanted to use math to predict verbal, the y-intercept would be your predicted verbal score when your math score is 0. Well, SAT math scores range from 200 to 800, so it's not possible to get a score of 0. So that's a case when the y-intercept would not be a valuable number to look at. You'll see some examples in the Wiley Plus homework this week, though, where the y-intercept could have some meaning. For the most part, though, what we're interested in testing is the slope. So the change in y for every 1 unit increase in x. We test the slope because the slope tells us if there is a relationship between x and y. So can x be used to predict y? In simple linear regression, that is tested via the slope. So when you do hypothesis testing, you're almost always going to be testing the slope. So b sub 1, or the value that is attached to that x variable. In terms of hypothesis testing for simple linear regression, again, the sampling distribution is going to be approximated using a t-distribution with n minus 2 degrees of freedom. Minitab Express and most other softwares provide only a two-tailed p-value. If you have a research question that's one-tailed, so if you want to know if the slope is greater than 0 or less than 0, you would divide the given p-value by 2 to get the one-tailed p-value. You'll also learn how to construct a confidence interval for a slope this week. Recall the general form of a confidence interval, the point estimate, which is your sample statistic, plus or minus the multiplier, this is the value that you're going to get from a t or a z distribution, times the standard error. The confidence interval for the slope is going to follow the same general form. Here, our point estimate is the slope in the sample. For the multiplier, we're going to use a t-distribution with n minus 2 degrees of freedom. And the standard error is the standard error of the slope, which Minitab Express will compute for you. Finally, the coefficient of determination, also known as r squared. This is a measure of practical significance. For correlation or regression, this is your measure of effect size. It is literally r squared. Every semester I get a lot of questions about how do you compute r squared. It is the correlation coefficient, or r, squared. By definition, r squared is the proportion of variation in y explained by variation in x, and vice versa. In other words, it's the proportion of shared variance between x and y. This concludes the Lesson 12 overview. As always, if you have any questions as you are working through this lesson or as you're preparing for the final exam, please post them to the discussion boards on Canvas.